Hello and welcome to today's lesson on an introduction to thermal physics, which is part of the thermal physics topic in AQA A-level physics. So in today's lesson we're going to try and understand and apply the concept of internal energy. So if we've been successful and learned in today's lesson, we should be able to describe what the difference is between heat and temperature, link the idea of internal energy to potential and kinetic energy, and then finally use equations to calculate internal energies, which links into the following part of the AQA A-level physics specification, 3.6.2.1 thermal energy transfer. Now, to fully understand the concepts in thermal energy, you've got to have a comprehensive understanding of the particle model of matter. Now, the particle model of matter shows the different formations of particles in the different states of matter. Now, the particle model of matter is good for approximating the properties of solids, liquids and gases. Now, when particles change state, the particles that make them up change the way that they are arranged, as shown in the following image. Now, it's actually better to show the particle model when looking at the movement of the particles, as this also allows you to show the energies that the particles possess in the different states. So you can see the movement and energy possessed in a gas, a liquid and a solid. So let's just recap very quickly the particle model of matter. So in a solid, the particles are arranged in a regular fixed structure. They can't move from their position in the structure, but they can vibrate. So in solids, we say that there's a high force of attraction between the particles, but little movement of particles. The particles in solids will only vibrate. Whilst in a liquid, the particles vibrate and are free to move around, but are still in contact with each other. The forces of attraction between them are less than when they're in a solid form. So in liquids, there's moderate forces of attraction and moderate movement of the particles. Whilst in the particle model of matter for gases, the gas particles are free to move randomly in all directions with high speeds, and there are almost no forces of attraction between them. So in gases, there's very little forces of attraction and very high movement of particles. Now, if we understand the particle composition of solids, liquids and gases, we can start to consider the principles of thermal physics. Now, as we're working on a particle level, this shows that thermal physics contains many assumptions and many approximations. So we're not considering the idea of nuclei or protons, neutrons and electrons, we're just considering particles as a solid sphere. Now, the assumptions that you use in your particular calculation, which you state in your answer, are just as important as the answer value itself. All thermal physics is an example of what we call statistical physics. We assume that we are dealing with many particles. Now, when a substance is heated, the particles will move or vibrate faster as the average kinetic energy in the particles has increased. So we can say that temperature is a measure of the average kinetic energy of the particles in a substance. For example, a substance at 24 degrees Kelvin would have particles on average with less kinetic energy than a substance at 200 degrees Kelvin. Now, as we can show in the following graph, we can look at how the temperature of a gas links to the average kinetic energy or speed of the particles in that substance. So a substance with a high temperature means that the particles are vibrating or moving with higher speeds on average compared with the substance at a lower temperature. Now, it's important to note that as kinetic energy is a scalar term, the fact that the different particles are moving in different directions is irrelevant, which is why particle speed is always discussed in thermal physics and not particle velocity. Now, if we use the Kelvin scale for temperature, the temperature directly links to the kinetic energy and the speed of the particle. So therefore 0 degrees Kelvin means that the particles will have an average kinetic energy of 0. Now you can see it in the following particular animation. At 0 degrees Kelvin or absolute 0, their particles have an average kinetic energy of 0, they are at rest. So we can say that temperature is a measure of the average kinetic energy of the particles in a substance. Now we can use classical mechanics because the particle model relies on the Newtonian laws of motion. So from the idea of classical mechanics, we can say that temperature is directly proportional to the average kinetic energy of the particles. So therefore temperature is directly proportional to 1/2 times by mass times by average speed squared. Now there is a physical constant which links the temperature of a substance with the average kinetic energy of the particles in the substance, which is called the Boltzmann constant, which we'll look at later. Now, as we go back to this following graph, this graph shows the distribution of particle speeds for a gas. Now, it's important to note that the particles in a gas do not travel at the same speed, and the speed distribution of the gas particles, as you can see on the graph, depends on the temperature. Some particles will be moving fast, but others will be moving much more slowly. But most of the particles in the gas will travel around at the average speed. Now, this is important because it shows us a few key ideas when we look at the different temperatures and the distribution speeds in a gas. So it tells us that firstly, as the temperature of a gas increases, the average particle speed in the gas will also increase. Again, as the temperature of the gas increases, the average kinetic energy of the particles inside the gas will also increase. And finally, as the temperature of the gas increases, the distribution or spread of the particle speeds in the gas will also increase. You'll have a bigger difference between the fastest moving particles in the gas and the slowest moving particles in the gas. Now, to consider this idea of temperature, we've got to consider what scale temperature is measured at. Now, the most common example in the United Kingdom is the Celsius scale, which was established by giving the temperature at which water becomes ice a value of 0 degrees Celsius and the temperature at which it boils at a value of 100 degrees Celsius. Now, using these fixed points, the Celsius scale was created. So the Celsius scale depends on the properties of a substance that we've chosen for our convenience, water. It's not very scientific, it's not very absolute. If water was not the most common substance on Earth, there would be no logical reason for choosing this to base our temperature scale on, which is why we've got to use a more absolute scale of temperature, which is the concept of Kelvin. And this is why measuring temperature in Kelvin is vital in thermal physics. So just to recap, to produce any temperature scale, you've got to use at least 2 fixed points to make a range of the scale. So the common example is the Celsius scale. The Celsius scale is based on the properties of water. So a thermometer is placed in water when it's at freezing point, and we define this as 0 degrees Celsius. The thermometer is then placed in water when it's at boiling point, and we define that at 100 degrees Celsius. So we've got our boiling point and freezing point. So this sets the scale of the temperature. So we say 1 is at 0 and 1 is at 100. So the space in between these points is then divided into 100 parts to get 1 degree. Now, this is a completely non-scientific and non-fundamental way to set a scale. So therefore, it's a bit of an abstract scale. So all temperature scales which are not Kelvin do not have a basis in fundamental science. Now, the method used to derive the Kelvin scale was actually derived from fundamental properties of gas. So in 1848, William Thomson, who was later honoured by Queen Victoria and called Lord Kelvin, came up with the Kelvin scale for temperature. So he measured the pressure caused by gases at known temperatures and plotted the results. And for every gas, he found a graph like this one. Now, by extrapolating his results, he found a temperature at which a gas, in theory, would exert 0 pressure. You can see the points which he's taken experimentally with the dots and the blue line, and then the extrapolation back to when it would exert 0 pressure. Now, it's important to note that for this extrapolation, we're assuming that the laws of physics are constant at all temperatures, which thankfully is true, but Kelvin didn't realise this. Now, since pressure is caused by the collisions of the gas particles with the container, 0 pressure means the particles are not moving and therefore have no kinetic energy. So when the particles exert no pressure, the particles have stopped moving completely, and we call this temperature absolute 0. It's not possible to get any colder. Now, on the Celsius scale, this temperature is minus 273 degrees Celsius. Now, this temperature has never actually been reached by scientists currently. However, it's hypothesized to be the lowest temperature possible in our universe. So this value of minus 273 degrees Celsius is called absolute 0 because it's the lowest temperature possible. Now, as the Kelvin scale of temperature is absolute 0 is 0 degrees Kelvin. Now, in the Kelvin scale, the energy of the particle is proportional proportional to the temperature of the substance it is part of. So at absolute zero, the particles of the substance are stationary because they have no kinetic energy. Now in this definition, we are ignoring movement due to quantum mechanical effects. So actually a better definition of absolute zero is when we say the internal energy of a substance is only potential energy because the kinetic energy store is zero. So the absolute zero is when the internal energy of a substance is at its minimum. Now, just to clarify, 1 Kelvin is the same size as 1 degree Celsius, but the Kelvin scale starts at absolute zero. So to get into your degree Celsius from Kelvin, you would do the Kelvin minus 273, whilst to getting Kelvin from degree Celsius, you would do degrees Celsius plus 273 equals your value in Kelvin. Now this is verified as the line between temperature and gas pressure always cuts the temperature axis at minus 273 degrees Celsius. Regardless of the gas used or the amount of gas used, it always cuts at the same point. Now in the previous statement we talked about internal energy. Now in the particle model we should consider all forms of energy stored in a particle structure. Now as well as the average kinetic energy of a substance, which links to the temperature, there is also a potential energy stored in the substance due to the forces of attraction between the particles in a substance. So there's a potential energy stored between the particles in a substance, which is due to the intermolecular forces of attraction between the particles. And there's also the previously mentioned kinetic energy store found in the particles of the substance due to the particles moving. Now in the particle structure, you've got these two energy stores, the kinetic energy store and the potential energy store. Now we refer to these together as the internal energy of the substance. So the internal energy is equal to the kinetic energy store plus the potential energy store. But it's important to note that it has to be for all of the particles in the substance. So the internal energy of matter is equal to the kinetic energy of all particles plus the potential energy of all particles. So to summarize these ideas, the particles within a substance all possess kinetic energy, which is due to their random motion. The particles also contain potential energy due to the chemical bonds and intermolecular forces of attraction holding them together and the bonds within their nuclei. The sum of all these kinetic and potential energies found in each particle represents the body's internal energy. So it is equal to the kinetic energy store plus the potential energy store. Now changing either the kinetic energy or the potential energy causes the internal energy to change. Now the formal definition of internal energy of a substance is that the internal energy of an object is the sum of the random distribution of the kinetic and potential energies of its molecules. So increasing either the potential or the kinetic energy store or both will result in an increase in internal energy. Now it's important to note that the internal energy store is a combination of the potential and the kinetic energy stores, and these stores are internal to the system and they're not combined with external stores. So don't confuse the kinetic energy of the particles with the kinetic energy of the object itself moving. Now, it's important to note that changing kinetic energy changes the internal energy store. Now, changing the kinetic energy occurs when the temperature of the substance changes. Now, by that same token, changing the potential energy store changes the internal energy store of the substance, which occurs when the object changes state. So this leads to a fundamental law of physics, that the change in internal energy of the object is the total energy transfer due to work done on the object and heating. So work done is placing energy into the system to change either the potential or the kinetic energies, which is what we call the first law of thermodynamics. Now when applied to objects, the direction of the energy transfer is very important, as it determines whether the internal energy of your object goes up or down. So energy can be changed between particles in a substance. Now if a substance is not heated or cooled, it acts as a closed system. Now a closed system is one where there's no transfer of matter or energy in or out of that defined system, in this case the substance itself. So this means the substance has a constant internal energy. Now in this concept, energy is constantly transferred between the particles within a system through collisions between the particles. However, the total combined energy of the particles remains unchanged. So you've still got that constant internal energy. Now the energy of an individual particle can change in the system with each collision, but the total internal energy of the system remains unchanged. So this leads to an important consequence of thermodynamics. The average speed of the particle will stay the same provided the temperature of the closed system stays the same and no work is done on the system. But the internal energy can be increased by heating it or doing work into the system to transfer energy into the system, e.g. by changing its shape. This will cause the average speed of the particles to increase. Now by the same effect, internal energy can be reduced by cooling the system or by doing work to remove energy from the system. Now the average kinetic energy and or potential energy of the particles will decrease as a result of energy being transferred out of the system. So, for example, when a substance changes state, it can change the amount of internal energy in its structure. As you can see here, when you've got ice, water and steam, and you can see that the internal energy of the substance is changing as it's changing state. Now it's important to note that work can be done in two ways to a system. Firstly, work can be done to change the kinetic energy store of a material, which will change its temperature. This physics is covered by something called specific heat capacity. And work can be also done to change the potential energy store of a material, changing its state. This physics is covered by the latent heat, and we'll cover these concepts in the next lesson on the course. So let's summarize what we've looked at in today's lesson. Internal energy is the sum of the randomly distributed kinetic and potential energies of the particles in a body. The internal energy of a system is increased when energy is transferred to it by heating or when work is done on it, or vice versa. So we've got the idea of the first law of thermodynamics. We've also got an appreciation that during a change of state, the potential energies of the particles are changing, but not the kinetic energies. So if we've been successful and learnt in today's lesson, we should be able to describe what the difference is between heat and temperature, link the ideas of internal energy to potential and kinetic energy, and use these equations to calculate internal energy. So thank you very much for watching today's lesson on an introduction to thermal physics, which is part of the thermal physics topic in AQA A-level physics. Thank you very much for watching and have a lovely day. Hello and welcome to today's lesson on specific heat capacity, which is part of the thermal physics topic in AQA A-level physics. So in today's lesson we're going to look at how you can calculate the specific heat capacity of a substance. So if we've been successful and learned in today's lesson, we can explain how work can be done into the internal energy of a system. We can define the specific heat capacity of a material, and we can measure the work done into the energy of a system using the internal energy of that system. So we're going to look at the following part of the AQA A-level physics specification, 3.6.2.1 thermal energy transfer. Now, when work is done to the internal energy of a system, that energy can be used to either increase or change the average kinetic energy of the substance, or it can be used to increase the average potential energy of the substance. Either one will change the internal energy. Now, if you change the kinetic energy of the internal energy, you'll be changing the temperature of the substance. If you change the potential energy store of the internal energy, you'll be changing the state of the substance. Now you'll notice in the diagram here we have a representation of the internal energy of a system. Now for most objects the potential energy store is larger than the kinetic energy store. So as we said before, if we increase the potential energy we can increase the overall internal energy. Now remember, changing the internal energy of the system is doing work. You must do work to change that internal energy store of a substance. Whilst also if if we increase or change the kinetic energy store of the substance, we will also be changing or increasing the internal energy. We'll be doing work again. Now remember, the change in internal energy is equal to the work done to the system. This is the first law of thermodynamics. Now in this lesson, we're only going to be focusing on how we increase or change the kinetic energy store of the internal energy of the system. Now an increase in the kinetic energy store of the internal energy would result in an increase in the temperature of the system, whilst a decrease in kinetic energy store would result in a decrease in temperature of the system. Now it's important to note that heat is always transferred from hotter substances to cooler substances. So heat energy is transferred from higher temperatures to lower temperatures. So the direction of work done is from an area of high temperature to an area of low temperature. Now this occurs because the particles with more energy transfers some energy to the particles with less energy. Now the higher the difference in temperature between the two substances, the faster the heat transfer between the substances. Now, as well as this idea of particles with more energy transferring some energy to particles with less energy, heat is also transferred by radiation. So hotter substances will radiate heat quicker than cooler substances, transferring that heat energy to the cooler surroundings. Now, when you heat a substance, the particles in the substance gain kinetic energy. So when we say heat is transferred into a substance, we say work is done into the system because the overall internal energy is increasing. Now, if we are placing heat energy into the substance, the kinetic energy of the particles increases. So therefore, the temperature of the substance itself increases. Now, doing work into or out of a substance will cause a temperature change in the substance. Now the equation that links work done in an internal system and the resultant temperature change of the substance is the following: delta Q is equal to mc delta T, where delta Q is the energy transferred, the heat transferred, the work done. M is the mass of the substance, C is the specific heat capacity, and delta T is the change in temperature of the substance. Now, carrying out work into the system, placing heat into or out of the system, causes a change in the kinetic energy store and thus the temperature. Now, it's important to note that delta Q is energy transferred or work done, so is measured in joules. The mass is measured in kilograms, and the change in temperature is measured in kelvins. Now, it's important to note that as this is a delta T, it's a temperature change, you can use either Celsius or kelvins to actually work out this value because the change in Kelvin and the change in Celsius is the same value. Now, the last thing we need to look at is specific heat capacity. Now, we can define heat capacity as the energy supplied to a substance to change the particle movement to make the temperature change by 1 Kelvin. Now, that is heat capacity. Now, specific means per kilogram. So, the specific heat capacity is the energy needed to raise 1 kilogram of a substance by 1 degrees Kelvin without changing state. So, just to clarify, the specific heat capacity is the link between the kinetic energy store change of the internal energy of the substance and the resultant change in temperature of the substance. Now, the larger the specific heat capacity of the substance, the more work is needed to be done to raise the temperature by 1 degrees Celsius or Kelvin. Now, the larger the specific heat capacity of a substance, the more kinetic energy is stored as internal energy per increase in temperature. So what this means is that an object with the highest specific heat capacity will store more kinetic energy per temperature change, so will have more internal energy. So if you have two materials which undergo the same temperature change, the object which has the higher specific heat capacity will store more internal energy. So this means that the object with the high specific heat capacity will have more internal energy, so will have a larger kinetic energy store and have particles moving on average at a higher speed. So let's now look at an example of a calculation with the specific heat capacity equation. So calculate the energy that must be supplied to raise the temperature of 5 kilograms of water from 20 degrees to 100 degrees Celsius. So the specific heat capacity of water is 4,200 joules per kilogram Kelvin. Now you will be given that in a question in your examination. Now the equation is delta Q is equal to mc delta T. Now you'll have noticed in this example I wrote delta T, the change in temperature, as T2 minus T1, the final temperature minus the starting temperature. We then put our values in. So 5.0 times by 4,200 times by 100 minus 20, which is 80. So we get our answer to be delta Q, the work done into the system, is 1.7 times 10 to the 6 joules. Now remember, as the temperature change is the same in degrees Celsius as it is in Kelvin, that means if you were given temperatures in degrees Celsius, then you can calculate the temperature difference in that particular unit. Now you've always got to remember as well to give your answers with the correct units and to the correct number of significant figures. And finally, always check to see if your answer looks sensible. Now again, remember the direction in which work is done into the particular system. Now because the temperature is going higher, it's going from 20 to 100 degrees, the work must be done into the system because the internal energy is getting higher, so we can say that's 1.7 times 10 to the 6 joules is being placed into the substance to cause this temperature increase. Obviously it will be the other way around if it was a temperature decrease. So let's summarize what we've learned in today's lesson. For a change in temperature, Q is equal to mc delta theta, where C is the specific heat capacity and in this case delta theta is the change in temperature. So if we've been successful and learnt in today's lesson, we should be able to explain how work can be done into the internal energy of a system. We can define specific heat capacity of a material and finally measure the work done into the energy of a system using the internal energy of the system. So thank you very much for watching today's lesson on the specific heat capacity, which is part of the thermophysics topic in AQA A-level physics. Thank you very much for watching and have a lovely day. Hello and welcome to today's lesson on continuous flow heating, which is part of the thermophysics topic in AQA A-level physics. So in today's lesson, we're going to look at how you can measure the specific heat capacity of a substance by using continuous flow heating. So if we've been successful and learnt in today's lesson, we should be able to explain how work can be done into an internal energy of a system. We can define the specific heat capacity of a material, then we can look at ways to measure the work done into the energy of a system using the internal energy. So we're going to look at the following part of the AQA A-level physics specification, 3.6.2.1 thermal energy transfer. Now the equation that links work done in an internal system and the resultant temperature change of the substance is delta Q is equal to mc delta T, where delta Q is the energy transferred, the heat energy transferred, m is the mass of the substance, C is the specific heat capacity, and delta T is the change in the temperature of the substance. Now carrying out work into the system, either placing heat into or out of the system, can cause a change in the kinetic energy store of the object internal energy and thus a change in temperature. Now let's just note that delta Q is measured in joules, mass is measured in kilograms, and delta T is measured in kelvins. But because delta T is a temperature change, you could actually also use degrees Celsius as well as Kelvin because the temperature change for Celsius and Kelvin is the same value. Now we can define the heat capacity as the energy supplied to a substance to change the particle movement of the particles that make it up to make a temperature change of 1 Kelvin. So the specific heat capacity is the energy needed to raise 1 kilogram of a substance by 1 Kelvin without changing state. So the specific heat capacity is the link between the kinetic energy store change of the object's internal energy and the resultant change in temperature of the substance that this causes. Now the larger the specific heat capacity, the more work is needed to be done to raise the temperature by 1 degree Celsius or Kelvin. Now the larger the specific heat capacity, the more kinetic energy which is stored as internal energy per increase in temperature. Now it's important to note that an object with a higher specific heat capacity will store more kinetic energy per temperature change, so will have more internal energy. So an object with a high specific heat capacity will store more kinetic energy per temperature change, so it'll have more internal energy. So the object will be a larger kinetic energy store and have particles moving on average at a higher speed compared to that object with a lower specific heat capacity. But how can we measure this specific heat capacity? Well, we can use something called continuous flow heating, and this is the process of heating a fluid by having it flow continuously over a heater. So what what you can see is that water flows into the substance. Okay, it then flows across the heater, and then the water flows out of the substance. Now, as the water or any fluid flows, the energy is transferred from the heater to the fluid. Now, we can therefore calculate either the specific heat capacity of the fluid, the work done by the heater, or the power of the heater. Now, it's important to note that calculations involving continuous flow heating can be simplified by assuming the heat transfer from the heater is 100% efficient. Now, this can be assured by making sure there's a good thermal contact between the heater and the fluid, which can be used by using a small amount of oil to lubricate the surface between the heater and the container the fluid is in. This can also be assured by making sure that there's little heat loss to the environment, which can be achieved by wrapping the fluid container in an insulated material called cladding. Now, what we're going to look at in this process is looking at calculating the energy transferred per second, or the power of the heater. So you can work out the power of the heater by doing the mass flow per second times by the specific heat capacity times by the change in temperature. Now, we can also use this to actually also work out the work done, or the energy supplied by the heater, or in fact the specific heat capacity of the substance. Now, what you do to do this particular calculation is you set up the experiment and let the water flow at a steady rate until the water out is at a constant temperature. Now, you would record the flow of water and the duration of the experiment, which allow you to work out the mass flow per second. You can then measure the temperature difference between the two thermometers before heating and after heating. Now, the energy supplied to the water we know is Q is equal to mc delta T plus H, where H is the energy lost to the surroundings. Now, what you would do in this particular investigation is you repeat the investigation for the heater on two different power settings, and then alter the mass flow per second to ensure that there's the same change in temperature for the fluid. So for the two experiments, we know that Q1 is equal to M1C times by delta T plus H, and Q2 equals M2C times by delta T plus H. Now, because we know that it's the same fluid, therefore C is going to be the same. We're going to assume that H is going to be the same, hopefully 0. And then we know delta T is the same because we've changed our experiment to ensure that delta T remains constant. So therefore we can say Q2 minus Q1 is equal to M2 minus M1 C delta T. We can say this because H is cancelled through, the delta T is the same, and the C is the same, so the only values that are changing are Q and M. So we can rearrange this equation and make C the subject. So we can say C, the specific heat capacity, is equal to Q2 minus Q1 over M2 minus M1 times by delta T, and that allows us to work out the specific heat capacity of the fluid via continuous flow heating. Now, you might say, how do you work out Q? Because Q is the energy transferred by the heater. Now, because it's an electrical heater, we can use an equation to work out the electrical energy transferred by the heater, which you've looked at previously in the electricity topic. So Q, the electrical energy transferred by the heater, is equal to V, the potential difference across the heater, times by I, the current through the heater, times by T, the time the heater is on. So that will allow you to work out the energy transferred by the heater. So you can therefore work out the work done, or energy transferred by the heater. You can work out the specific heat capacity of the fluid, or the power of the heater. So let's summarise what we've looked at in today's lesson. For a change in temperature, Q is equal to M times by C times by delta theta, triangle T, where C is specific heat capacity, and calculations can include continuous flow like we've looked at in today's lesson. So if we've been successful and learnt in today's lesson, you should be able to explain how work can be done into the internal energy of a system, define the specific heat capacity of a material, and then look at how you can measure the work done into the energy of a system using the internal energy. So I hope you've enjoyed today's lesson on continuous flow heating. Thank you very, very much for watching, and as always, have a lovely day. Hello and welcome to this lesson on latent heat, which is part of the thermophysics topic in AQA A-level physics. So in today's lesson we're going to look at understanding and calculating latent heat. So if we have been successful and learned in today's lesson, we should be able to detail the ways in which internal energy of a system can change. We can define and describe what the latent heat of a substance is, and then finally we can calculate values based on the latent heat of a substance, which links into the following part of the AQA A-Level Physics specification, 3.6.2.1 Thermal Energy Transfer. So in the particle model, we should consider all forms of energy stored in the particle structure. So you've got the average kinetic energy of a substance, which is links to the temperature, and there's also the potential energy stored in the substance due to the forces of attraction between the particles in the substance. So there's a potential energy stored between the particles in any substance, which is due to the intermolecular forces of attraction between the particles and the chemical bonds. There's also a kinetic energy store found in the particles of a substance due to the particles moving. Now together, these two energy stores are referred to as the internal energy of the substance. So internal energy is equal to the kinetic energy plus the potential energy. But to calculate the internal energy of the matter of the substance, we've got to consider the kinetic energy of all the particles and the potential energy of all the particles. So to summarize, the particles within a substance all possess kinetic energy. This energy is due to their motion, whilst particles also contain potential energy due to the chemical bonds and intermolecular forces of attraction holding them together and the bonds within their nuclei. The sum of all these kinetic and potential energies found in each particle represents the body's internal energy. So the internal energy is the kinetic energy store plus the potential energy store. Now changing either the kinetic energy or the potential energy store causes the internal energy to change. So the internal energy of an object is the sum of the random distribution of the kinetic and potential energies of its molecules. So increasing either the potential energy store or the kinetic energy store or both will result in an increase in internal energy. Now just to clarify, these stores are internal to the system and are not combined with the external stores of kinetic or potential energy a substance may experience. Now, changing the kinetic energy changes the internal energy store, which will cause the temperature of the substance to change, whilst changing the potential energy store changes the internal energy store also, but when you change the potential energy store, the state of the object will change. So this leads to a fundamental law of physics, that the change in internal energy of an object is equal to the total energy transfer due to work done in heating. So placing work into a system will change either the potential or the kinetic energy store, which is the first law of thermodynamics. Now when applied to objects, the direction of the energy transfer is very important as it determines whether the internal energy goes up or down. So when a substance is changing state due to heating, the potential energy store of the object will increase in the change of state. So as work is done into the system, energy goes into giving the particles more potential energy to break their bonds and lower the forces of attraction, such as going from a liquid to a gas. Now this doesn't make the particles vibrate anymore because the kinetic energy store is unaltered. So when you put work into the system, it will cause the potential energy store to increase, which causes the objects to separate. Now, it's the same idea when going from a liquid to a gas. So if we've got the idea of particles constantly vibrating, eventually the particles have enough potential energy stored to overcome their forces of attraction to move away from each other and jolt past each other. This will cause a change in state. Now, it's important to note that at this point, most of the potential energy stored then changes to the kinetic energy store. So after that state interchange, that potential energy store lowers. Now, we can also look at the idea of when an object changes state due to cooling down. Well, when this takes place, the potential energy stored will decrease, because as work is done out of the system, the potential energy stored in the particles is lost to the surroundings. Now, this doesn't make the particles vibrate more because once again the kinetic energy stores unaltered. So when work is done out of the system, you move into an even lower potential energy store. Now eventually the particles have lost so much potential energy stored, they succumb to their forces of attraction and will move towards each other, so they'll jolt together. So this will cause a change in state. Now when this happens, most of the kinetic energy store is changed to a potential energy store, so it means that after the state interchange, the potential energy store has increased. So let's just clarify. When work is done to the internal energy of a system, the energy can be used to change the average kinetic energy, so change the temperature, or change the average potential energy, change the state of the internal energy. Now in previous lessons we've considered changing the kinetic energy store, but now we're going to consider changing the potential energy store. Now it's important to note that for most objects in the internal energy, the potential energy store is larger than the kinetic energy store. Now again, if we change the potential energy store, we can change the internal energy. Changing the internal energy of a system is called doing work. So it's an important idea to consider. So let's consider what happens when we change the potential energy store of the internal energy of a system. So a change in potential energy store would result in a change of state. Now it's important to note that different substances require different amounts of work to be done to change them from a solid to a liquid to a gas, or any other state change. This is due to there being different forces of attraction between the particles given potential energy stores. So the forces of attraction are due to the size of the particles in the substance. This means that the mass of the particles affects the potential energy store. Now, in addition to that, the forces of attraction are different due to the different types of particles. This means that something called the latent heat capacity of a substance affects the potential energy store. So the work done required to change the potential energy store in the internal energy of a system is a combination of two factors. You've got the mass of the object and the specific latent heat or latent heat capacity. Now, delta Q represents the change in potential energy in the internal energy store and is measured in joules, whilst the mass is measured in kilograms, whilst the specific latent heat is measured in joules per kilogram. So L represents the specific latent heat, which is the energy required to change the state of 1 kilogram of a substance without a change in temperature. Now the more rigorous definition of specific heat capacity must now include without the change in temperature status. Now the specific latent heat of fusion is the energy required to change 1 kilogram of a solid into liquid, or vice versa, without a change in temperature, whilst the specific latent heat of vaporization is the energy required to change 1 kilogram of a liquid into a gas, or vice versa, without a change in temperature. Now the latent heat of vaporization needs more work to be done to be carried out compared to the latent heat of fusion, as the particles change position more going from a liquid to a gas, or vice versa, compared to a solid to a liquid. So this changes the forces of attraction more, so therefore more work is needed to be done. This is because the liquid and gas particle model are very different in configuration. So this means that there's a large change in the forces of attraction and more bonds are broken, so therefore there's a greater change in the potential energy store, giving a large latent heat. Whilst if you have a liquid to a solid, or vice versa, the liquid and solid particle models are not that different in configuration. So there's a smaller change in forces of attraction, so less bonds are broken, and the potential energy store changes less, so it gives a smaller latent heat. So this tells us that in fact that the latent heat of vaporization is a much larger value for a substance compared to the latent heat of fusion. So just to clarify, we define the latent capacity as the energy supplied to a substance to change the forces of attraction to make the substance change state. So the specific latent heat capacity is the energy needed to make 1 kilogram of a substance change without a change in temperature. So the latent heat is the link between the potential energy store change and the resultant change in state. So the larger the specific latent heat, the more work is needed to be done to change the state of a substance. So the larger the latent heat capacity, the more potential energy which is stored as internal energy per state change. So if you consider two materials undergoing the same change of state, an object with a higher latent heat capacity or specific latent heat will store more potential energy per state change, so will have more internal energy. So this means if you have a high specific latent heat capacity, this means that the object with a larger potential energy store and have particles of greater force of attraction will be the one with a higher specific latent heat. Now please remember that when the potential energy store changes size, there's no work done on the kinetic energy store in the internal energy of the system. So this means that when there's a change of state, there's going to be no change in temperature of the substance. This idea can be illustrated on a heating curve. So when a substance changes state, there's no change in temperature, which we can indicate on a heating or cooling curve by a flat line. So what happens is the energy goes into changing the potential energy store of the internal energy and not the kinetic energy store. So this tells us that this change in energy is hidden from the temperature observation, or it is latent, as latent is another word meaning hidden. Now we can identify a state change from a heating or cooling curve, like we said before, when there's a flat line, because when there's a change of state, there is no change in temperature, so the work is being done on the potential energy store. So when there's a change in temperature, there is no change in state. So you can see on this particular heating curve, where there are flat lines, there's a change in potential energy. Now you'll notice that when there's a change of temperature, we know that there's going to be no change of state, so as a result it's a change in the kinetic energy store of the object's internal energy, not a change in the potential. So you get either a change of temperature when your line is either going upwards or downwards, and you've got a change of state when the line is flat. So you've either got a change in the kinetic energy store, which is indicated by a change in the temperature, or you've got a change in the potential energy store, which is indicated with a change in state. Now when a solid is heated, work is done to make the particles vibrate more, which means that the temperature increases. Now at this point, because the temperature is increasing, the potential energy store of the solid remains constant, but the kinetic energy store increases. Now at the melting point, the particles don't vibrate any faster, meaning that the kinetic energy and the temperature are therefore constant. But the bonds that keep the particles in a rigid shape are broken, and the potential energy store increases. Now in liquid form, the particles are still in contact with each other, but can slide past each other. Now as more work is done, the particles vibrate more, so the kinetic energy store increases, but the potential energy store is constant. Now at the boiling point, the particles again don't vibrate or move any faster, meaning that the kinetic energy store and the temperature are constant, but the bonds holding the particles together are completely broken. Now what this means is that the temperature doesn't change, but the state does. Now this takes a lot more energy when this happens compared to melting, since all the bonds are broken. So therefore the latent heat of fusion is going to be less than the latent heat of vaporization. Now the same process is true if the substance is cooled down, because the physics of heating and cooling are identical. However, heating requires work to be placed into the internal energy of the system, whilst cooling requires work to be taken out of the internal energy of the system. So previously, we have stated that the internal energy is the amount of energy found inside of a system, made of two parts, the kinetic energy store and the potential energy store. But remember, the internal energy is a representation of all particles in the system. Now we can calculate the internal energy of a system by using the equation, the internal energy is equal to the kinetic energy plus the potential energy. Now the kinetic energy store can be looked at by thinking that a change in kinetic energy store is shown by a change in temperature, and this energy can be calculated by using specific heat capacity, whilst a change in potential energy store is shown by a change in state, and this energy is calculated by the specific latent heat. But remember, it's only true when we consider all particles in the system. So we can calculate the change in the kinetic energy store by doing delta Q is equal to m times by c times by delta T, where c is specific heat capacity. And we can calculate the change in the potential energy store by saying delta Q is equal to m times by L, where L is the latent heat. So we can therefore say the overall change in the internal energy is delta Q is equal to mc delta T plus ml, because you have your change in your kinetic energy store and you have your change in your potential energy store. Now because m is a common factor in both terms, we can factorize out m in the equation. So we can therefore say delta Q is equal to m times by c delta T plus L. So as a result, we can therefore work out mass quite easily. Now please remember that this equation is not the total internal energy of the substance, rather it is the internal energy change. Now let's just summarize what we've learned in today's lesson. So for a change of state, Q is equal to ml, where L is specific latent heat. Now if we've been successful and we've learned in today's lesson, we can detail the ways in which the internal energy of a system can change. We can define and describe what the latent heat of a substance is, and finally we can calculate values based on the latent heat of a substance. So thank you very much for watching today's lesson on latent heat, which is part of the thermal physics topic in AQA A-level physics. Thank you very much for watching and have a lovely day. Hello and welcome to the following lesson on experimental gas laws, which is part of the thermal physics topic in AQA A-level physics. So in today's lesson we're going to look at understanding and describing the experimental properties of gases. So if we've been successful and learned in today's lesson, we should be able to state the experimental gas laws, calculate an increase in pressure of a gas when it's heated or compressed, and then state what is meant by an isothermal change. So we're going to be looking at the following parts of the specification: 3.6.2.2 ideal gases. Now, to help define and understand the properties of a gas, consider a gas to consist of one particle in a box. Now in reality, a gas consists of billions and billions of particles in a box, which is just a container. Now the first property of a gas is the volume, which we denote with the symbol V, which is the space occupied by the particles that make up the gas. So in the example of it being a particle in a box, it is the space of the box. So the volume is measured in meters cubed. Now it's important to note that the volume of a gas is not the volume of the individual gas particles, rather it's the volume of space between the gas particles. Now gas particles can be considered to have a negligible volume compared to the volume of the actual gas itself. The second property of a gas is the temperature, which is the measure of the average kinetic energy of the particles in the gas, which in our previous example is the speed of the particle. Now we measure temperature in Kelvin. Now there's a directly proportional relationship between the average kinetic energy of a gas particle and the average temperature and the absolute temperature, of the gas. Now the absolute temperature of a gas is given when the temperature is measured in Kelvin. Now the third property of a gas is the pressure, which is given the symbol P. Now when a gas particle collides with the walls of its box, it causes a pressure. So pressure is given by the equation force over area. So pressure is the force per unit area exerted by the gas. Now pressure is measured in pascals, where 1 pascal is equal to a pressure of 1 Newton per square meter. Now pressure is caused by the collisions of the gas particles with the surface of the container it is in. It is not caused by the collisions of gas particles with each other, because due to their respective sizes, it's very unlikely that gas particles would collide with each other. Now when physicists realized that gases could have their volumes, their temperatures and their pressures measured, we could look at working out laws to link these quantities. Now these laws are called the experimental gas laws because the laws were devised from experimental results and they were not derived from theoretical discussion. Now in the 17th century, Robert Boyle published a paper linking two properties of gases: the pressure of a gas and the volume of a gas. So the linking of pressure and volume became known as Boyle's law. Now Boyle carried out his work with apparatus such as the following. Now it was found that for a constant temperature that the gas pressure and the volume of a gas are inversely proportional. So we could say P is directly proportional to 1 over V, or we could also write it as pressure times by volume equals a constant, which you can symbolize as PV equals constant. But please be aware, like mentioned before, this equation only works when the temperature is constant, as the temperature of the gas can affect its pressure and volume. So we refer to this law as an isothermal change, because iso means the same and thermal means temperature, so saying that's an isothermal event indicates that the temperature has not changed. Now this idea of pressure and volume for a gas being inversely proportional links into our model of a particle in a box, because if the temperature is constant, it means that the particle in the box is travelling at a fixed constant speed. So what this means is if we increase the size of the container of the box, that the gas particle has fewer collisions in the same time with the sides of the container, because it has to travel further before it collides with the slide. So the bigger box that the gas is in, the fewer collisions with the surface, whilst the smaller the box, the more collisions with the surface, because if we make the box that the gas is in smaller, the gas particle will collide with the box more often, since it has less distance to travel at the same speed. So this shows us that for a constant temperature, the pressure and volume vary with each other. So as pressure increases, volume decreases, and vice versa. So pressure and volume are inversely proportional to to each other. Now we say that any gas that follows Boyle's law is an ideal gas. A gas at a very high pressure does not obey Boyle's law. So the gas is no longer ideal as the molecules are so close to each other that the molecule's own volume now becomes significant. So our experimental results for Boyle's law follow the following pattern. So we can see it in this particular graphical representation, that the pressure and the volume are inversely proportional. So when one value increases, the other value decreases by the same factor. Now it's important to note that this particular graph can be repeated for any temperature as long as it's kept constant throughout the investigation. Now what we tend to find is the higher the temperature of the gas, the steeper the gradient of the line, as shown in the following graph. Now these are still isothermal changes since the temperature is fixed throughout the investigation. Now we can also plot pressure against 1 over volume, which gives us a straight line through the origin. So we can now see that when we say y equals mx plus c, that p is going to be the value for y, 1 over v is the value for x, given our constant as m. So in this graph, the gradient of the line gives you your Boyle's law constant. Now the second law is called Charles's law, because 100 years later in France, Jacques Charles used the work of Boyle to see if he could produce a flying machine. Now Charles was convinced that the properties of gases, hydrogen in particular, was key to humans flying. So in 1783, Charles carried out the first manned hydrogen balloon flight in history. Now in 1787, Charles did an experiment where he filled 5 balloons to the same volume with different gases. He then raised the temperature of the balloons to about 80 degrees Celsius and noticed that they all increased in volume by the same amount. Now this was true when he used when he changed the temperature by the same value and he measured it in an absolute scale such as Kelvin. Now he noticed this was true for all types of gases as well. So in fact this experiment was referenced by Guy Lussac in 1802 when he published a paper on the relationship between the volume and the temperature of a gas. Now Charles' law states that under constant pressure an ideal gas's volume is proportional to its absolute temperature. So V is directly proportional for T. So when the pressure on a sample of gas is held constant, the temperature in kelvins and the volume of the gas will be directly related. So it was found that for a constant pressure that the gas volume divided by the gas temperature is a constant value for each gas. So we can say that volume over absolute temperature is equal to a constant, but only when the temperature of the gas is measured in Kelvin. Now once again, this follows our model of a particle in a box, because if the pressure is constant, it means that there's the same number of collisions of the gas particle with the side of the container every second. So what this tells us is if we make the box bigger, then the gas molecules would have to move faster to then make sure you have the same amount of collisions every second. So therefore the gas particle must move faster to collide the same number of times, so the temperature must be going up. And if the box was made smaller, the molecules have to move slower to make sure there's the same amount of collisions per unit time, so the gas particles are moving slower to have the same number of collisions every second, so the temperature is going down. So this shows us that as the volume increases, the pressure increases, so they're in direct proportion. Now once again, we say that any gas which follows Charles' law is an ideal gas. Now any change where the pressure stays constant, such as in Charles' law, we say is an isobaric change, because iso means the same and baric means pressure. So the experimental results for Charles' law follow this particular pattern. Now notice that measuring the volume and absolute temperature of a gas gives a straight line through the origin. Now the gradient is the proportionality constant between the two, and it's important to note that this shows V and T are directly proportional because the graph is a straight line through the origin. Now when work is done to change the volume of a gas, energy must be transferred by heating to the gas to keep that pressure constant. So we can also say that work done is equal to pressure times by change in volume. So work done is equal to the pressure times by that change in volume, and you can work this this out experimentally with the following bits of equipment. So what you would do is you would heat a substance, okay, normally with sulfuric acid. The volume of the gas in the syringe would be measured, the temperature of the flask is measured, so you would vary your value of temperature and you would measure the volume of the gas to then see if you can derive Charles's law with experimental values. Now when you graph Charles' law, it was found that the volume of a gas always became zero at minus 273 degrees Celsius or 0 Kelvin. So Charles' law was the first to predict the existence of absolute zero, the lowest possible temperature in the universe. Now at certain temperatures the gases had no volume. Now why was this? Well, this is because the particles do not move, so therefore cannot collide with the surface, and as the particles themselves have no volume, therefore as a result there's going to be no pressure, there's going to be no volume. So therefore the gas has no volume when it has no movement of particles. Now it was important to note that this temperature of absolute zero was found to be the same for every gas in the universe. Now originally the value of absolute zero was extrapolated from experimental values at much higher temperatures. Now when the law was first devised by Charles, it was ignored because it was postulated that the law only worked for high temperatures and this law did not hold true for low temperatures. It was only William Thomson or Lord Kelvin who realized what this meant and devised absolute zero. Now as you will realize from the graphs, as the x-intercept of a volume temperature graph gives you absolute zero, the graphs of volume temperature are slightly different when the different temperature scales are used. So the graph on the left hand side is when the temperature is given in the Kelvin scale, while the graph on the right hand side is when the temperature is given in the Celsius scale. So the x-intercept in the left hand side graph is given at 0 Kelvin, whilst the x-intercept on the right hand side is given at minus 273 degrees Celsius. Now the last law is the pressure law, where it was postulated that the pressure of a gas of fixed mass and fixed volume is directly proportional to the gas's absolute temperature. So what this means is that if a gas's temperature increases, then so does its pressure if the mass and the volume of the gas are held constant. So this law has a very simple mathematical form if the temperature is measured on an absolute scale such as Kelvin. So P is directly proportional to T, or we could also say that pressure over absolute temperature, P over T, is equal to a constant, but it only is true if the temperature is given in kelvins. Now again, this follows our model of a molecule in a box, because if the volume in it is constant, it means that the box has a fixed size. So if we increase the speed in which the molecule is moving, it will hit the side of the box more often. So when the temperature increases, the gas particles are moving faster, giving more collisions a second, increasing the temperature. Now if we slow the molecule down, it will hit the sides of the container less often. So when the gas particles move slower, it has a lower temperature, so therefore there are less collisions every second, so the pressure is lower. So what this tells us is that as the temperature of a gas increases, the pressure of the gas increases. There's a directly proportional relationship. So the experimental results for the pressure law follow the following pattern. Now we can show this in graphical form as well. So you can see P plotted against T. Now again, measuring the pressure and absolute temperature of a gas gives a straight line graph through the origin, where the gradient is the proportionality constant between the two. Now again, this shows that P and T are in direct proportion as it is a straight line through the origin. Now again, this is only true if the volume is kept constant throughout the investigation. Now again, as the x-intercept of a pressure temperature graph gives absolute zero, the graphs are slightly different when different temperature scales are used. So on the left hand side we've got when the temperature is given on the Kelvin scale, and on the right hand side when the temperature is given on the Celsius scale. Once again, our x-intercept in the Kelvin scale is at 0 Kelvin, whilst our x-intercept in the Celsius scale is at minus 273 degrees Celsius. So let's summarize what we've learned in today's lesson. We can state the experimental gas laws derived by physicists when examining gas behavior. Now in these laws, temperature must be stated in Kelvin. The first law is Boyle's law, which is an isothermal change law, where PV is equal to constant, or you could say P1V1 equals P2V2, or the change in pressure over pressure equals the change in volume over volume. The second law is Charles' law, where you can say that V over T is equal to a constant, or V1 over T1 is equal to V2 over T2, or the change in volume over volume is equal to the change in temperature over temperature. This law is an isobaric change because pressure must be kept constant. Now we can also work out the work done when you change the temperature of a gas by doing work done is equal to pressure times by change in volume. Now our final law is the pressure law, which says that P over T is equal to a constant. We can also say this is P1 over T1 is equal to P2 over T2, or the change in P over P is equal to the change in T over T. Now this law is true for constant volume. So for the gas laws, any of these interpretations can be used to solve problems. So to summarize, we should be able to have the gas laws as experimental relationships between P, V and T and the mass of a gas. Now if you've been successful and learnt in this lesson, you should be able to state the experimental gas laws, calculate the increase of the pressure of a gas when it's heated or compressed, and state what is meant by an isothermal change. So I hope you've enjoyed today's lesson on the experimental gas laws, which is part of the thermal physics topic in AQA A-level physics. Thank you very much for watching and have a lovely day. Hello and welcome to the following lesson on the ideal gas equation, which is part of the thermal physics topic in AQA A-level physics. So in today's lesson, what we're going to do is try and understand and describe the ideal gas equation. So if we've been successful and learnt in this lesson, we should be able to define what an ideal gas is with its assumptions, discuss whether the experimental gas laws can be combined and if so how, distinguish between molar mass and molecular mass, and then finally use the ideal gas law to solve problems with gases. So we're going to be looking at the following part of the AQA A-level physics specification, 3.6.2.2 ideal gases. Now the three experimental gas laws are as follows. Boyle's law, which is where pressure times by volume is equal to a constant, i.e. pressure and volume for a gas are inversely proportional. The second law is Charles's law, which is volume over temperature is equal to a constant. In this case, volume and temperature are directly proportional. And finally, you've got the pressure law, which is pressure over temperature is equal to a constant, i.e. that the pressure and temperature for a gas are directly proportional. Now we can take these three experimental gas laws and we can combine them into one equation, which is that P times by V over T for a gas is equal to a constant. Now this constant is just a value which links these three properties for any gas. Now we can then use this to then derive a very useful equation to compare the pressure, volume and temperature of a gas from when it's changed from one state into another. So it's an equivalent. So we can say P1V1 over T1 is equal to P2V2 over T2. Now please remember, in this equation and for every equation we look at in this lesson, the temperature in this equation must be given in kelvins. Now for this particular equation to be used, we've got to make an assumption, and we've got to say that the gas is acting as an ideal gas. Now this is one version of the ideal gas law. Now this version should be used if you're evaluating a change or a difference in a property of a gas. Now you might ask, what is an ideal gas? Now an ideal gas is a theoretical gas that obeys the experimental gas laws at all pressures and temperatures. Now in this case, the internal energy of an ideal gas is only dependent on the kinetic energy of its particles. The particles do not have any potential energy. So whilst we say an ideal gas is one that obeys Boyle's law and Charles's law and the pressure law under all conditions, in reality no real gas is an ideal gas under all conditions. Under the conditions of low pressure and high temperature, real gases will obey Boyle's law and behave in an ideal manner. But if you have a high pressure or low volume and temperatures near to a gas's boiling point, real gases stop behaving ideally and no longer follow Boyle's law. The reason why this is because in these conditions the gas's molecules or atoms occupy a significant proportion of the gas's overall volume, which means it can no longer be acting as an ideal gas. Now it's important to note that the particle model of matter always shows an ideal gas view of a gaseous state. But remember, this is an assumption, and gases are not actually ideal. Now, ideal gases have several key assumptions attached to them. Now, here are the ideal gas assumptions. Number 1, all gas particles are identical to each other. Number 2, all particle motion in a gas is continual and random. Number 3, all particle motion in a gas follows a straight line. Number 4, all molecules in a gas have a negligible volume compared to the volume of the container, i.e. the container that the gas is in is much bigger than the particles of the gas themselves. Assumption number 5 is that the gravitational force and the electrostatic force between gas particles does not exist. Number 6, the internal energy of a gas has no potential energy store, only a kinetic energy store. Number 7, the Newtonian laws of motion are obeyed by particles in their motion, and there's enough molecules in a gas to apply statistical laws. Number 8, all particle container collisions are elastic, so when particles collide with the container that they are in, the momentum and the kinetic energy of those particles is conserved. And finally, the time between each collision with the container surface is much longer than the duration of a collision for particles in a gas. So, when describing an ideal gas, we assume the gas has the following properties, which is to ensure we can derive an equation to describe the property of a gas. The molecules of a particular gas are all identical. The internal energy of the gas is entirely kinetic. All collisions between molecules and the walls of the container the gas are in are completely elastic. Newton's laws of motion apply. The molecules take up negligible volume of the gas. Gravitational and electrostatic forces can be ignored. The motion of all molecules is random, and all the molecules travel in straight lines. Now, like mentioned before, in reality, no gas is ideal, so it's a mathematical assumption we use to make the formulas of ideal gases easier to handle. So, like we mentioned before, we can combine the 3 experimental gas laws into one equation. PV over T equals a constant. Now, ideal gases all behave in the same way, so we can say that they'll all have the same constant, and we can assign a letter to this constant, which we can give as R. Now, R is what we call the molar gas constant. Now, R has a value of 8.3 joules per Kelvin per mole for all ideal gases. So this tells us that if the volume and temperature of a gas are kept constant, then the pressure depends on R and the number of particles in the container. So we can then therefore say, we can write this in our equation by saying PV over T is equal to nR, where n is the number of moles in the gas. Now we can rearrange this to give the standard form of the ideal gas equation, which is PV is equal to nRT, where R is the molar gas constant and is 8.31 joules per Kelvin per mole for all ideal gases. T is the absolute temperature of the gas in kelvins, P is the pressure of the gas in pascals, V is the volume of the gas in meters cubed, and N is the number of moles in a gas. Now, what do we mean by the term mole? Now, a mole is the amount of a pure substance containing the same number of chemical units, either molecules or atoms, as there are atoms in exactly 12 grams of carbon-12, which is 6.023 times 10 to the 23. So basically, a mole is a measure of how many particles there are. So 1 mole is when there are 6.023 times 10 to the 23 atoms or molecules or particles of a substance. So a mole is just a term used in language to describe an amount, like the term single, double or triple would be. So there are many examples of getting 1 mole of a substance. So you can see on the following images 1 mole of that substance. Now, different atoms or molecules of different substances are different sizes and masses. This is why different molar amounts can be different sizes and masses as shown in these particular images. These are all 1 mole of that particular substance. Now, in 1811, the Italian scientist Amedeo Avogadro developed a theory about the volume of gases. So Avogadro's law states that equal volumes of different gases at the same pressures and temperatures will contain equal numbers of particles, i.e. the same number of moles. So if you have the same volume of a gas, you'll have the same number of moles of a gas. So in mathematical terms, Avogadro's law is V1 over N1 is equal to V2 over N2. So we can express the number of moles in a substance mathematically. We can say that the number of moles in a substance is equal to the mass of the substance divided by its molar mass. Now the molecular mass is the sum of the masses of all the atoms that make up a molecule of the gas. Now this is given on the periodic table as the relative atomic mass, e.g. the molecular mass of carbon-12 is 12. Now this can also be called the relative molecular mass when there are a number of atoms in the gas molecule. Now this links to the molar mass because the molar mass is the mass that 1 mole of a substance would have. Now when this is given in grams, the molar mass is the same as the relative molecular mass for a molecule. So for example, the relative molecular mass of O2 is 32. So this means that the molar mass of O2 is 32 grams. But please be aware that the molar mass can sometimes be needed in a question in kilograms instead of grams. So just be mindful of this. Now you can also write this equation in another form. We can say that the number of moles is equal to N over Na, where N is the number of particles or molecules in a substance and Na is Avogadro's constant, 6.023 times 10 to the 23. Now you can use either of these two equations to work out the number of moles in a substance. It's dependent on the quantities you are given in a question. Now the concept of ideal gases is then used to approximate the behaviour of real gases. Now obviously real gases can become liquids at low temperatures and high pressures. So we can use our Avogadro's equation to derive a new equation for an ideal gas. So like we said before, PV is equal to nRT, but we just looked in our previous examples of another equation for N. So we can then write that and substitute it in. So we can substitute in the value in our equation we use for moles and Avogadro's constant by now saying PV is equal to the number of molecules times by R times by T over Avogadro's constant. Now again, you can use either equation to work out a value of a gas. It's dependent on the quantities you're given in your puzzle. Now remember, if you are going to use either of these two equations, the temperature must be given in kelvins. So let's have a look at an example. A cylinder contains 400 moles of an ideal gas at a temperature of 290 Kelvin. If the volume of the container is 8 meters cubed, what is the pressure of the gas? So to answer this type of question, you would follow the following steps. So step 1, you would write out the ideal gas equation you would need to use with the values given in your equation. In this case, PV equals nRT. Step 2, rearrange the equation into the actual value you want to work out. In this case, pressure, P. So P is equal to nRT over V. Then step 3, ensure the temperature is given in Kelvin. Yes it is, and sub in your values. So 400 times by 8.31 times by 290 over 8. You can then step 4, calculate your value to be 1.20 times 10 to the 5 pascals or 120 kilopascals. Now it's also important to notice that a scientist called Ludwig Boltzmann noticed that R and Na, which were given in our previous equation of PV is equal to nRT over Na, are both constants, so dividing one by the other will always give the same value, which he called the Boltzmann constant. Now the Boltzmann constant is the physical constant relating energy at the individual particle level with temperature, but it's important to note we can only ever work this out at a collective or bulk level because it's a statistical value, it's an average value. Now we represent the Boltzmann constant with the symbol K, and we can work it out by saying K, the Boltzmann constant, is equal to R, the molar gas constant, over Na, Avogadro's constant. Now all these constants, K, R and Na, are given to you in your examination formula booklet. Now K, the Boltzmann constant, is 1.38 times 10 to the minus 23 joules per Kelvin. So what that is telling you is that basically when you raise the temperature by 1 Kelvin, each individual particle will receive an extra 1.38 times 10 to the minus 23 joules worth of energy. Now remember, you can only use the Boltzmann constant when considering many particles. It's an example of statistical mechanics value. It's only true as an average of many particles. So we can then use this equation to then simplify our previous ideal gas equation. So when dealing with with individual molecules of a gas, we can use a different constant because the molar gas constant is only applicable for n number of moles of a gas. So we can now say PV is equal to nKT, where n is the number of molecules of the gas and K is the Boltzmann constant, the gas constant for a single molecule. So our Boltzmann constant has now replaced the values of R and Na in the equation. So there are actually many forms of the ideal gas equation. Our most standard form, PV is equal to nRT. The form which has Avogadro's constant in, PV is equal to nRT over Na. The equivalence form, which is used when you've got a change in the value of a gas property, P1V1 over T1 is equal to P2V2 over T2. And finally, the Boltzmann form when you're considering the individual gas molecules themselves. PV is equal to nKT. Now please remember these are all iterations of the same physics principle, the ideal gas equation. Now you can use any form of this equation in an ideal gas question, you've just got to look at the values given in your problem. So let's summarize what we've learned in today's lesson. The ideal gas equation is PV equals nRT for n moles and PV equals nKT for n molecules. You should be aware of the Avogadro constant Na, the molar gas constant R, and Boltzmann constant K, and also be aware of the terms molar mass and molecular mass. So if we've been successful and learnt in today's lesson, you should be able to define an ideal gas with all of its assumptions, discuss whether the experimental gas laws can be combined and if so how, distinguish between molar mass and molecular mass, and finally use the ideal gas law to solve problems with gases. So I hope you've enjoyed today's lesson on the ideal gas equation, which is part of the thermal physics topic in AQA A-level physics. Thank you very much for watching, and as always, have a lovely day. Hello and welcome to today's lesson on molecular kinetic theory, which is part of the thermal physics topic in AQA A-level physics. So in today's lesson we're going to try and understand the molecular kinetic theory for gases. So if we've been successful and learned in this lesson, we can describe the behaviour of a gas, we can discuss what the mean kinetic energy of a gas molecule depends upon, and also calculate the root mean square speed of a gas. So it links into the following part of the AQA A-level physics specification, 3.6.2.3 molecular kinetic theory model. So in previous lessons, we've considered the concept of a gas. Now we can consider a gas in two ways. In the microscopic way, which considers the gas on the particle level, and the macroscopic way, which considers a gas as how we interpret from our physical senses. So when we consider the microscopic, we are thinking that a gas is made out of identical particles which move in random directions in a linear motion. The gas particles have a negligible volume, no potential energy due to electrostatic attractions, and they obey Newton's law of motion. Now the gas particles themselves have a speed of motion which links to the temperature, and they have a pressure which is due to the elastic collisions they have with objects, and these gases can be explained by the ideal gas laws. But when we consider the macroscopic interpretation of a gas, we state that a gas is a state of matter which does not seem to interact with objects easily. Now gases do have measurable physical quantities such as pressure, temperature, mass, the number of moles and weight. Now the gases can be explained on a macroscopic level by the experimental gas laws. PV equals constant, V over T equals constant, and P over T equals constant. Now the kinetic theory of gases links the macroscopic behavior of a gas with its microscopic behavior. So like we said before, in macroscopic terms, a gas is a phase of matter that has a fixed mass and whose volume is equal to the volume of the container, and the gas exerts pressure on the walls of the container, whilst in microscopic terms, a gas is a collection of many particles that collide with each other and with the container walls. Now the molecular kinetic theory relates the pressure exerted by a gas to the motion of its particles. So in today's lesson we're going to examine the molecular kinetic theory and deduce values from it. Now like we just said, gas pressure is caused by gas particles colliding with the container it is in. Now the amount of pressure produced is dependent on the rate of change of momentum caused by the gas particles. Now one of the ways you can change the rate of change of momentum is the number of collisions per second. Now the higher the number of collisions per second, the greater the pressure. So lots of collisions every second, the higher the pressure. Now, the other way we can consider it is, as well as having the number of collisions every second, the rate of change of momentum is also dependent on the force of the collisions. The higher the force of collisions with the container, the higher the pressure. So if a gas particle collides with lots of force in the collision with the container, the pressure will be high. So the gas pressure is related to the rate of change of momentum acting on the surface, which is linked to both the number of collisions per second and the force of the collisions. Now, both these factors, the number of collisions per second and the force of collisions, is dependent on the speed of the particles. This shows that the pressure exerted by a gas is dependent on the speed of the particles. Now, the speed of the particles also relates to the temperature of the gas. So what we know is that speed of gas particles is linked to the temperature of a gas. The higher the temperature of a gas, the faster the particles move. But do you think that all of the particles in a gas in a certain container will move at the same speed? Well, the particles do not move at the same velocity. The temperature is a measure of the average velocity of a particle, not its individual speeds. So the particles do not move at the same velocity. So it's important to note that gas particles move with a variety of speeds in random directions. So it's important to note that there's a variety of speeds in any gas. Now, this is represented by something called a Boltzmann distribution curve. Now, the higher the temperature of the gas, the more spread out the distribution of those speeds. So the higher the temperature, the greater the average speed of the particles. So the temperature relates to the average speed of the particles in the gas. So you'll see on here our Boltzmann distribution curve. So this is a graph showing the probability an individual particle will have a particular kinetic energy and speed depending on the temperature of the gas. So as mentioned before, we call this a Boltzmann distribution curve. Now, as we mentioned before, the higher the temperature of a gas, the more spread out the distribution of those speeds. That's because there's more possible energy states for the particles to be in at that higher temperature. So the higher the temperature, the more particles with a higher speed. Now, as well as that, okay, we can also notice that there's a variation in particle speeds because the particles collide with each other and the container that they are in, which means that the kinetic energy in the entire gas is not evenly distributed amongst the particles, allowing those variations in speed. Now, but you've also got to remember though that the area under the curve is going to be the same for each temperature. So whilst the higher the temperature, the more spread out the distribution and the greater the number of particles at higher speeds, the total area will be the same regardless of the temperature for a gas. This is because the total probability for all possible speeds and states is the same for each temperature, so the area must be the same. That's because the kinetic energy is going to be staying constant, it's just going to be changing how distributed it is. Now, like we said before, there's a variety of speed in any gas, and the higher the temperature, the more probable it is that the particle has a higher kinetic energy. Now, this occurs as it's assumed that there are many gas particles in the sample, and it allows for statistical mechanics to be considered for this particular sample. Now, this shows that if we want to understand how we can work out the temperature and pressure of a gas, we need to consider how to calculate the speed of the particles in a gas. So, when we talk about the speed of gas particles, we are actually referring to the mean velocity of the gas particles. Now, when gas theory discusses speed, it actually refers to velocity, which is going to be a speed with a direction. Now, as gas particles move in a random motion, there's no preferred direction for particle movement. So you'll notice that gas particles will move in any particular direction, which means that if the motion is random, it means that the directions of the particles would cancel each other out. So ultimately, that the average velocity or the average speed in gas theory would always be zero, which means we've got to use a different value to represent the velocity of a gas. So just to clarify, at a constant temperature, the speeds of individual particles will not remain the same. They change as they collide with other particles and the container they are in. However, the distribution of speeds in the entire body of gas will remain the same, as will the average speed. Now, this is the sum of all the speeds divided by the total number of particles. Now, for a gas at every temperature, if you just did the average speed, it would give you a zero value due to the random motion of the gas. So therefore, instead of using the average speed, we've got to look at the root mean square speed. Now the root mean square speed, which is given as CRMS of molecules, is different from the average speed. Now you'll notice in the root mean square speed equation, it is the square root of particle 1 speed squared plus particle 2 speed squared plus particle n speed squared over the total number of particles. So it's the entire term which is square rooted, not just the top line. Now this then gives you a value which cancels out that idea of direction which comes from the velocity concept. So let's look at an example of how you would calculate the root mean square speed of particles. So if you had these three speeds, these three molecules moving with these different speeds, what would the average speed of the molecules be? Now the average speeds of the molecules will be 0 meters per second. This happens as the gas is carrying out random motion, so the directions of the molecules will cancel out, giving you a 0 velocity. But what would the root mean square speed of the molecules be? So what you would do is you would do the square root of those speed values squared and added together divided by the total number. So it would be 2000 squared plus 3000 squared plus 7000 squared divided by 3 all square rooted, which gives you 4546 or 5000 meters per second. This now takes out the idea of the random direction of the gas particle motion. Now we're going to use the idea of root mean square speed of particles in a gas to link to the pressure produced by a gas. So what we're doing is we're linking a microscopic idea of particle speed to the macroscopic idea of pressure exerted. So to do this, we've got to consider the gas particles to be made out of identical particles and therefore be an ideal gas. So what are our assumptions when we consider a gas to be ideal? Well, an ideal gas is one that obeys Boyle's law and Charles's law under all conditions. Now in reality, no real gas is an ideal gas under all conditions. However, we do have some assumptions regarding gas particles if we do think they are ideal. First one, all the gas particles are identical. Number two, all particle motion is continuous and random. Number three, all particle motion follows a straight line. Number four, all molecules have a negligible volume compared to the volume of the container that they are in. Number five, the gravitational force and the electrostatic force between the gas particles does not exist. Number 6, the internal energy of the gas has no potential energy store, only a kinetic energy store. Number 7, the Newtonian laws of motion are obeyed by the particles in their motion, and there are enough molecules to apply statistical laws. Number 8, all particle container collisions are elastic, so momentum and kinetic energy is conserved in every collision, and that the time between each collision with the container and the surface is much longer than the duration of a collision. So when describing an ideal gas, we assume the gas has the following properties, so we can actually derive equations with the behaviour of this gas. So all the molecules of the gas are identical, the internal energy of a gas is entirely kinetic, all collisions between molecules and the walls of the container are completely elastic, Newton's laws of motion apply, the molecules take up negligible volume, the gravitational and electrostatic forces can be ignored, the motion of all molecules is random, and all molecules travel in straight lines. Now, like we said before, in reality, no gas is ideal, so it's a mathematical assumption to make the formulae easy to handle. So we can use these assumptions to derive an equation for the behaviour of an ideal gas. So let's consider with an ideal gas assumption that the molecules move in all directions. So let us start with the molecule of mass m travelling with the velocity vx, so it's travelling in the x-plane, but could be any direction. So it collides with the walls of the container. Each wall has a length L, as you can see in the diagram. Now, if we consider the collision between the particle and the container, we'll consider it to be an elastic collision, which is an assumption of an ideal gas. So we note that it will hit off the container starting with the velocity of plus Vx and then leave with the velocity of minus Vx. Now, there are different signs of the velocity as the particle is moving in different directions. Now, the one we assign as positive and negative is arbitrary because it just comes down to particular perspective. So we'll say going into the wall is the plus and going away from the wall is the negative, but it doesn't make a difference. Now we can now calculate the change in momentum. Now beforehand it's plus Vx and afterwards it's minus Vx. So the momentum is mass times by velocity, so it's plus mvx minus mvx. So the change in momentum is plus 2 mvx. So that's an important idea. Now we also know that force is equal to the change in momentum divided by time. So force is equal to 2 mvx over time. So to make this equation more meaningful, we now need to derive a value for time between the collisions. So if we consider a particle moving in linear motion throughout its journey in the container, which is an ideal gas assumption, we've already said it's going to be moving in the x plane because it's got a velocity of vx. So we can use the speed equation to determine the time between collision 1 on one side of the container compared to collision 2 on the other side of the container. So this means we can calculate the time between successive collisions by using the equation distance over speed. We know that speed is vx and the distance is twice the length of the box because it's gone from one side of the box to the other side, collided with the wall and gone back to where it's originally started. So we can say that time is distance over speed, so the distance is 2L, twice the length of the container that the particle is in, divided by its speed, vx. Now remember, our assumption here is that it's carrying out linear straight line motion, which is an ideal gas assumption. So we can pop this equation for time into our force equation. So we can say change in momentum over time is equal to 2 mvx over 2L divided by vx. So we can now rearrange this to a more friendly format. So we can now put the vx's on top and then we can cancel and collect the terms. So we can now say that force is equal to mvx squared over L. So what this gives us is the force of one molecule acting on the side of the container. So we can now use the force exerted in a collision between the particle and the container to determine the pressure of the gas. So we've got our equation for force and we know that force is equal to pressure times by area. So pressure is force over area. So we've now subbed in our value for force of mvx squared over L divided by the area. Now we know for this particular cube that the area must be L squared because it is, the boxes are all length L. So therefore pressure is going to be mvx squared L over L squared. So we can now say that L cubed, which is going to be, which we found we collect the L terms together, is just the volume. So pressure is equal to mvx squared over L cubed, which is V. So therefore we can only carry out this assumption if the container is a cube. So now we can consider our equation for pressure. So this means we can use the root mean square speed to consider the average speed of all the particles. So now we can say pressure is equal to mv hat squared x over V. So where V in that case is the volume. Now remember, the average kinetic energy is constant, not the individual particle kinetic energy due to particle collisions. So now let's consider, that's just for one particle. Let's now consider the total pressure from all particles n. So the pressure now is going to be big N, the number of particles, times by m over V hat x squared divided by the volume. Now that's just in one plane. That's just in the x plane. But remember, we've got to consider the pressure in all three dimensions because gas is 3D. It's in the z plane, it's in the y plane, and it's in the x plane. So as well as having Vx in the speed in the x plane, you're going to have Vz, the speed in the z plane, and Vy, the speed in the y plane. So therefore the mean total speed in all directions is going to be given by c hat, or c average, is equal to V hat x plus V hat y plus V hat z. So why we've put that hat on is because now we're considering the average speed. So therefore we can say that c hat squared is equal to Vx squared hat, V squared y hat, and V plus V squared z hat. So now what we can say is that c squared hat is equal to 3 V squared x hat. Now the reason why we can collate Vx and Vy and Vz to be the same term is because in theory the particle motion is random. So that means the speed, there's an equal chance of speed in the x and the y and the z direction. So we can assume in our ideal gas that the velocity values Vx, Vy and Vz, so therefore V squared x and V squared y and V squared z are all the same value. So we can just collate it into 3V squared x. I mean, we could say it's 3V squared y or 3V squared z, but we've been using x since the start of the equation, so it's better to use those terms. And again, the hat is there just to ensure we're using our average speed. So now we can rearrange and make V squared x hat the subject. So we've now previously determined our equation for particle speed. And we've got our equation for pressure as shown previously. So all we can do now is we can then rearrange the equation and place P and V together, like in the ideal gas equation. We can then substitute in the equation for the root mean squared speed for all directions. So V squared x hat is equal to C squared hat over 3. And therefore what we can then do is then make it a bit nicer to look at and say PV is equal to 1/3 NM hat, mc squared hat, which is our kinetic theory equation. So for an ideal gas, we have the kinetic theory equation, which can be written as the following. PV is equal to 1/3 NMC RMS squared, or PV is equal to 1/3 NMC hat squared. Now that's the same thing. CRMS and C hat are the same thing. It's the root mean square speed of the particles. Remember, we've got to use that because particles have random motion. So if we just use the average speed, it would equal 0. M is the mass of the gas in kilograms. N is the total number of particles in the gas, and they're all identical because it's the ideal gas assumption. V is the volume of gas in meters cubed, and P is the pressure of the gas in pascals. So this is the kinetic energy equation of an ideal gas. It links the macroscopic properties of a gas with the microscopic properties of a gas. So you've got the macroscopic terms such as PV, and you've got the microscopic terms 1/3 NMC RMS squared. So it links the two concepts together. Now we can use the kinetic theory equation to work out other quantities. So for an individual particle of gas with mass m traveling at speed c, its kinetic energy is going to be Ek is equal to 1/2 mc squared, which is the equation you know previously. Kinetic energy is 1/2 mv squared, but we're saying the speed is going to be given by the symbol c in this context. So this can be used to work out the mean kinetic energy of a gas particle by using the following equation. So we know that the mean kinetic energy of one particle is going to be equal to the total kinetic energy divided by the total number of particles. So the mean kinetic energy is going to be 1/2 mc1 squared plus 1/2 mc2 squared up until 1/2 mcn squared divided by n. So what we're doing is we're going to work out the total kinetic energy by summing the individual particle and kinetic energies. So therefore what we can do is we can then take 1/2 m out to factorize it, because it's going to be a constant term in all those particular individual particles when we're working out the kinetic energy. So we can now say the mean kinetic energy is equal to 1/2 m open bracket c1 squared plus c2 squared plus c3 squared plus cn squared, and then divide that by n. So this gives us an equation for the mean kinetic energy of one particle in a gas. So now we can say actually what we're doing is we're going to be needing to use the root mean squared speed. So we can now say that the mean kinetic energy is going to be equal to 1/2 mc RMS, the root mean square speed, squared. Now finally, as the temperature of an ideal gas increases, so does the mean kinetic energy of the particles. We talked about that at the start of the lesson. So we can equate these two equations. PV is equal to nRT and PV is equal to 1/3 NMC RMS squared. So you can link the two together. Now it's important to note that big N, the number of particles, is just the number of moles, small n, times by Avogadro's number. So therefore we can substitute that in, and the number of moles on each side of the equations cancels through. So we get now RT is equal to 1/3 NAMC RMS squared. But we know that 1/2 MC RMS squared is equal to the mean kinetic energy. So on the right hand side of the equation we can take that out and just put in EK. So now what we can say is RT is going to be equal to 2/3 NAEK. But we also know that K is equal to R over NA, so we can take that out. So therefore we can say that KNAT is equal to 2/3 NA mean kinetic energy. Now there's an NA on both sides of the equation. So ultimately now you get that the mean kinetic energy is 3/2 kT. So we can therefore say that the kinetic energy of one gas particle in a gas is equal to 3/2 times by the Boltzmann constant K times by the absolute temperature. That's when the temperature is given in kelvins. So this equation links the microscopic property of a gas particle, its kinetic energy, with the macroscopic property of temperature. So this shows us that the properties of a gas can be approximated to it being caused by collisions of small sphere-like particles with the container that the gas is in. So if we say that the mean kinetic energy of one particle of an ideal gas is 3 over 2 kT, we can then use this to consider the total kinetic energy of 1 mole of an ideal gas. So what we could then say is, if we've got that one particle has a kinetic energy of 3 over 2 kT, we times that by the number of particles in 1 mole, which is Avogadro's number, which is 6.023 times 10 to the 23, which is Na. But we also know that K is equal to R over Na. So therefore what we can say is that the kinetic energy of 1 mole is equal to Na times by 3 over 2 R over Na times by T. The two Na's cancel through, so therefore our total kinetic energy of 1 mole is equal to 3 over 2 RT. So this means that the total kinetic energy of n moles of an ideal gas is going to be 3 over 2 nRT, where n is the number of moles, R is the molar gas constant, and T is the absolute temperature. So to summarise, the kinetic theory leads to the following equations, which links the particle or microscopic nature of a gas with the experimental or macroscopic nature of a gas. And these equations can be used in any thermal physics problem. PV is equal to 1/3 Nm CRMS squared. The mean kinetic energy of the gas is equal to 1/2 mCRMS squared. The mean kinetic energy of one particle is going to be 3 over 2 kT, and find the total kinetic energy of n moles of an ideal gas is 3 over 2 nRT. Now for these equations we assume the particles are identical, they have random motion, they have linear motion, they have no potential energy store, the particles have no gravitation or electrostatic attraction, the particles move under the Newtonian laws of motion, and the particles undergo elastic collisions. So if we have learned in today's lesson, we should be able to have an explanation of the relationships between P, V and T in terms of a simple molecular model, understand that the gas laws are empirical in nature while the kinetic theory arises from theory, the assumptions leading to PV is equal to 1/3 nmCRMS squared, including the derivation of the equation and calculations, a simple algebraic approach involving the conservation of momentum, and appreciation that for an ideal gas the internal energy is the kinetic energy of the atoms, and that for average molecular kinetic energy it's 1/2 mCRMS squared, or 3 over 2 kT, or 3 RT over 2 Na. So if we've been successful and learnt in today's lesson, we should be able to describe the behaviour of a gas, discuss what the mean kinetic energy of a gas molecule depends upon, and finally calculate the root mean squared speed of a gas. So thank you very much for watching today's lesson on the molecular kinetic theory, which is part of the thermal physics topic in AQA A-level physics. Thank you very much for watching, and as always, have a lovely day.